Then it's my pleasure to announce the second speaker, Vlad Alexandru Silvestru from ETH Zurich. He received his PhD from TU Graz and has worked as a facade engineer afterwards at Luchinger Meyer in Zurich, and has now moved on to ETH as a researcher and lecturer there. And he will present a very nice topic of pre-stressing glass beams through shape memory alloys. So, Vlad, it's yours.
Thank you, Christian, for introducing me, and good morning, everybody. I will discuss today about some concepts for pre-stressing glass beams with iron-based shape memory alloy. And in my presentation, I will first start with a brief background on reinforced and post-tension glass beams, and also introduce you to this iron-based shape memory alloy, which is actually the innovative part of these glass beams that we investigated. I will then present you some results from a feasibility study where we looked at medium-scale 4-point bending, so where we performed medium-scale 4-point bending tests on such beams. And finally, the content that is also described in the paper, I will present you the model characteristics for the finite element simulations that we conducted, and also the different concepts at which we looked at. And finally, draw some conclusions and give you some outlook.
Can I fix a little bit?
Yeah.
There you go.
Thank you. Is it better now? Yes. So to give you a background, laminated glass beams are usually used in facades or for transparent roofs to support the structure. And you have here two examples. A little bit of difference is that in facades, you always will have for sure tension along both edges because you have wind suctions, wind pressure. In the case of roofs, you might have tension only on the bottom side if the dead weight is high enough that you don't have uplifting. However, if we look at the laminated cross-section of such a beam under bending, we will be able to carry load until we have a first crack. And afterwards, we have just a low residual load-bearing capacity, depending on the interlayer that is used. This is how it would look with annealed glass. With heat-strengthened glass, it looks similar. In our studies, we focused on annealed glass. Previous research tried to improve this behavior by adding a ductile tendon on the tension side. And in this case, on the one hand side, the initial cracking resistance can be increased. And furthermore, the post-cracking behavior can be improved. However, if we look into real projects, these systems were not really applied a lot. There are, in my opinion, two reasons. One is that architects and also clients usually want to see the free glass edge. The other reason is probably that, especially for post-tensioning, the approaches used are quite complex. So here comes into play the iron-based shape memory alloy that I mentioned. And this kind of shape memory alloys are materials that are able to remember their shape after two-phase transformations. And as you can see in this short video, for the iron-based shape memory alloy, the first transformation is triggered by deforming, and the second one by heating. So when you heat it, it wants to go back into the initial shape. In our studies, we used the product Memory Steel, which was developed by EMPA and Refer AG, especially for construction applications. And in recent years, it was used mainly to strengthen existing concrete or steel structures, as you can see in these two examples. So you have the predeformed strips or rods. You fix it mechanically to a parent structure. And afterwards, when you heat it, it would like to go back. However, it's fixed, so it will apply a pre-stress on the parent structure. And we thought this is a quite easy way to apply pre-stress. Why not look if it's possible to apply it for glass beams? So in our experimental study, we said, OK, we bond the strips to the glass edges by adhesives along the whole length of the edge. We heat them in a defined area called activation area in order to not disturb the adhesive in the anchorage areas. And afterwards, after it cools back down to ambient temperature, we have a post-tensioned or pre-stressed structural element. Of course, as I mentioned in the introduction, depending on your loading situations, you could apply the strips along both edges or only along one of the edges. This would result, of course, in a different pre-stress state with a uniform stress or with a linear stress distribution. I will now present you some results from the bending test that we performed. So we looked at medium scale tests, mainly for cost reason and also because it was a feasibility study. We had simply supported beams in 4-point bending, and the length of the beams was 1.5 meters, the span 1.4 meters. And we tested we tested also beams without any tendons for reference, so simple laminated glass beams, and then also beams with a tendon as a reinforcement but not activated, as well as beams with the activated tendons. You can see here the geometry of these beams. The glass was made of 3 times annealed glass with centric glass interlayers, and the adhesive that was used in the results that I'm showing you was the 2-component epoxy Zika Power. We also looked at an acrylate. However, in the study that I'm presenting today, I'm only focusing on these adhesives. For the pre-straining, for the activation, as well as for the test, we had some strain gauges to monitor the strains in the middle of the glass at different positions. And for the activation, we also used a high number of thermocouples to monitor the temperature on the glass surface, as well as on the shape memory alloy strips. You can see here the setup that we used for activation. We did it by so-called electrical resistive heating, which means we apply an electrical current. You see it on the left side with these copper clamps. The current flows to the right side, is diverted to the bottom strip, and flows back to the left side. And the idea is that the current and also the heating happens only in this middle part of the beam, not in the anchorage areas, so the adhesive there is not disturbed in any way. If we look at the temperatures and the strains that we monitored, you can see in the left, on the diagram on the left-hand side, the temperatures. The dashed line, so the black dashed line, where you see it's constant, so no temperature increase, was on the shape memory alloys in the anchorage area. So this confirmed that the adhesive there will work perfectly. If we look at the glass, we had some heating there, but these are the blue curves, but it was quite low, so we didn't have any problems with thermal stresses. Looking at the strains, so if I go one slide back, we had strain gauges over the height of the beam. So if we look in the beginning of the activation, the strains were not uniform, but over time, so after it cooled back to ambient temperature, we had a uniform strain there, which corresponded to a compressive pre-stress of around 7 megapascal. I have to say that we applied the electric current to reach a target temperature in the shape memory alloy strips, which was defined to 160 degrees in this case. You could increase it further theoretically, but then you really have problems with adhesive there. So it's like a compromise. I'm just showing you a small detail about the activation. So if we look at the first 3 minutes and you look on the right diagram, the glass first expands when you hit it, like it's normal for almost every material. However, at around 50 degrees, the shape memory alloy, the phase transformation is triggered in the shape memory alloy, and starting with that point, the glass starts to compress. In terms of test results, I will show you 2 videos. One for the classical laminated glass, so you have a first crack, and then if you increase the displacement, so the tests were displacement controlled, you will be able to increase the displacement until also the interlayer will fail. If we look at the post-tensioned glass beam, we have a first crack, then we have a lot of additional cracks. And if you look at the top part of the beam of the glass, this is still intact. So this is like qualitatively to see what happens. In this case, there is no failure because we had to stop the test at 10 centimeters deflection due to safety reasons. I will now show you also some numbers from this test. So if we look at the reference beams, we were able to reach a force at the initial glass crack of around 8 kilonewtons. And the corresponding tensile stress that we measured with the strain gauges, so corresponding to the strains that we measured with the strain gauges was around 43 megapascal, which is quite well in the range of the characteristic strength for annealed glass. However, after this initial crack, the force dropped to around 1/3, and we were also able just to reach quite low displacements or small displacements until the ultimate failure. For the reinforced beams, we were able to increase the initial glass crack force. So these are the beams with tendons, but non-activated ones. So we were able to significantly increase the force at initial glass crack. And interestingly, we also had stresses when this crack happened quite significantly higher than the strength of the annealed glass, than the expected strength of the annealed glass. And also after the initial, so after the primary crack, we were able to carry quite high loads for a long amount of time. For these beams, just with tendons that were not activated, we had tendon rupture at the end. However, if we look at the ones with activated tendons, we were able to further increase the initial glass crack. So this is mainly the advantage of the post-tensioning. But afterwards, the behavior was pretty similar to the beams without activation. And here, as I said, we had to stop the tests at 10 centimeters deflection. So to conclude about the tests, this showed that the concept that we introduced works well. We didn't see any negative influence of the adhesive because it was heated in the middle part before the test. So during activation, we saw very locally some delamination. So we thought, okay, it would be nice to also look at some different concepts, maybe without adhesive or adhesive just in the anchorage part. And for that, we developed a finite element model in Abacus based on different literature references that are available. We used Abacus explicit for it, and the mesh looks very detailed at the bottom because here we expect the cracks, and it's a little bit coarser along the top edge. For the activation part, we used, so we assumed cooling along the middle parts of the strips with predefined fields in Abacus, and we calibrated the cooling temperature based on so to reach the same strains in the system as we measured in the experiments I presented before. Then the loading was applied displacement controlled displacement controlled, but the speed we had to increase with a scaling factor to reach reasonable computation times for this kind of simulations. In terms of materials, I will not go into a lot of detail. You have the details in the paper. We used for all other materials then, except for the glass, elastic plastic models based on values from our own previous tests or from literature. For the glass, we used an elastic material model including this brittle cracking model from Abacus. For these, you have to define a failure stress. And here, for the simulation of the test that we performed, we assumed the failure stress for 70 Newton per square millimeters, although we had annealed glass, because it was the value that we measured with the strain gauges in the test. And what this model also includes is these properties for brittle shear, brittle failure. The brittle shear is considering the shear modulus of the cracked glass beam, and the brittle failure defines that the elements in which this failure stress is reached are removed from the system. So yeah, and for the interactions, we assumed tie constraints between the adhesives because we didn't see any failure due to loss of adhesion in our tests. So with this model, we were able to predict quite well the results we observed from the tests. So we see also so before the initial crack, a good prediction, but also the post-cracking behavior was predicted quite well, including the occurring cracks. So after validating the model, we decided to look at different concepts based on finite element simulations, and we assessed also concepts with strips only along one side, only along the bottom edge. Also systems, these two look quite similar. The difference is that in the middle part, there is no adhesive, so we have adhesive only in the anchorage areas. And then also systems with mechanical anchorage, because I'm now attending conferences for glass like for the last 10 years, and the trend for adhesive connections is somehow going downwards, at least that's my feeling, probably because of the whole reuse topic. So we thought, are we able to achieve similar results without using the adhesive, only with mechanical anchorage? And for this, the strips are fixed to steel blocks, which are positioned at the end of the glass beams, and the pre-stress is actually then introduced through some grouting at the ends of the beams. So if we look now at the results for the concepts with two-sided shape memory alloy strips, in the activation for the beams with adhesive anchorage, we have the pre-stress only in the middle part, as you can see here. For the one with the mechanical anchorage, since we introduced the forces at the end of the beams, we have a pre-stress over the whole length of the beam. If we look at the values, we can observe that actually the beams that we first tested experimentally with adhesive bonding along the whole length of the edges performed best. So there you can reach the highest pre-stress. For all these beams, the pre-stress was applied in the simulations by cooling, so we cooled them with the same temperature. Maybe an addition between the one with adhesive bonding along the whole edge and the one with adhesive anchorage, we had higher local stresses for the one where we didn't have adhesive in the middle part. For the concepts with one-sided strips, the trend in terms of values was similar, so we could pre-stress it the most if we have adhesive bonding along the whole length. And what we observed on the bottom edge, we were able to reach a higher pre-stress value if we have the strip only on one side. But as I said before, this works if you have a beam in a glass roof or something like that, where you don't have where you don't expect tension along both edges. If we look at the force displacement curves for these different types of beams, we can directly see that the ones with adhesive bonding along the whole length of the edges, so this is the black curve, reach higher forces. But this is especially because of the assumed failure stress for the glass. So for the black curve, we assumed this higher stress value based on the strains that we measured in the experiments. For the other type of beam, since we don't have adhesive in the middle part where the crack will occur, we expect that the failure stress will stay in the range of the characteristic strength of the annealed glass. And for the ones with one-sided strips, the results look pretty similar. These large drops, so these larger drops, in the case of the first crack, these are due to the time scaling factor that we used in the simulation. If we would reduce the loading speed in the simulation in that range, this drop would disappear at some point. So this is like a dynamic effect that we have there. And yeah, finally, I would like to also show you the cracking behavior for the concepts with two-sided strips, the cracking behavior that we observed for the different concepts. So we can see the initial crack looks pretty similar. We have between our two So we have the 4-point bending load. So between our two loads, we have the initial cracks. And then when we load it further, for the one with bonding along the whole length, we have several cracks distributed. For the one where we don't have adhesive in the middle part, so the main crack will just get larger and larger. I'm now coming to the conclusions. Based on the experiments that we performed, we showed that post-tensioning laminated glass beams with full-length adhesively bonded strips allow a significant increase of the initial glass fracture force, and it's also possible with these systems to reach a ductile failure mode. Based on the increase of the initial force, we could also imagine that we could reduce the cross-section of the glass beam with this system, so we would use less material. The mechanical anchorage or adhesive bonding only for anchorage allow only smaller increase of the initial glass fracture force, but they also allow a good residual load-bearing capacity. So you reach after fracture, you can still carry the whole load also with these systems. And as an outlook, the simulations could be used also to assess further systems and also to include other aspects like initial geometric imperfection, lateral torsional buckling. And of course, when we see one of the systems performs best, it should still be validated by experiments, and open question is definitely the long-term behaviors, including the adhesive and to the pre-stress. So with this, I would like to thank you for your attention. I would also like to acknowledge the partners who supported us financially and also with material, especially for the experiments. And if there are any questions, I'm happy to try to answer them. Thank you.
Thank you very much.